Good afternoon, ladies and gentlemen. This is Mohammad Mehdi Hassan, lecturer, Department of Mechatronics Engineering from Rajshahi University of Engineering and Technology. Along with me, we have Afifa Akhtar and Mohammad Samir Yamin as moderator to provide any sorts of technical support to this session. Today, we are in the second day of 2021 International Conference on Automation, Control, and Mechatronics for Industry 4.0. Current time is 2 p.m. Bangladesh Standard Time. I would like to welcome all of you in the keynote session number 7 of ACMI 2021. On this special occasion, we feel proud to have Dr. Raad Raad, Associate Professor, University of Wollongong, Australia, as an invited speaker. ACMI 2021 has got a new dimension to have a resourceful person like him. So dear audience, this is the time to welcome our honorable keynote speaker, Dr. Raad Raad, with big round of applause.
Thank you so much.
Thank you for your appreciation. It's our immense pleasure to have Professor Dr. Masuma Akhtar ma'am from Dhaka University of Engineering and Technology, Bangladesh as chair, and Dr. Muhammad Hassan Imam from American International University, Bangladesh as co-chair of this keynote session. After the end of the keynote presentation, there will be question and answer session. All the audiences are requested to write questions, if any, in the chat box. Audience can also raise hand up in Zoom after the end of the presentation. Now I would like to request our honorable chair and co-chair to take the floor and introduce our honorable keynote speaker to the audience. Thank you.
Thank you, Mohammad Mehdi Hassan. As me, I am Dr. Masuma Akhtar, Professor, Department of Electrical and Electronic Engineering, Dhaka University of Engineering and Technology, Gazipur. Honorable guests, respected audience, welcome to this keynote session in the conference 2021 International Conference on Automation, Control, and Mechatronics for Industry 4.0. The title of this keynote session is 5G and Internet of Things from Space with Advanced Antennas for 5G Enabled Mega Constellations. This technical session will be conducted by Associate Professor Dr. Raad Raad. Here I introduced him in very shortly. Associate Professor Dr. Raad Raad received his Bachelor of Engineering degree in Electrical Engineering from the University of Wollongong in 1997. He received the Australian Postgraduate Award and Tesla in Research Laboratories Scholarship, which allowed him to complete a PhD degree entitled Neurophagy Logic Admission Control in Cellular Mobile Networks in 2006. He worked for Tesla and Motorola Research Laboratories, and since 2004, he has been with School of Electrical, Computer, and Telecommunication Engineering, University of Wollongong, where he serves as the deputy head of school. His current research interests include wireless communication, CubNet, the IoT, and antenna designs. I welcome Dr. Raad Raad to start his keynote sessions. Dr. Raad Raad, the floor is yours now. I welcome him.
Thank you so much for that introduction. And hopefully everyone can hear me okay. Maybe give me a thumbs up if everything's okay. Yes. Thank you for the gracious invitation. Thanks for that, Mehdi. Thank you for giving me the time to share with you some of our work here at the Wireless Technologies Laboratory at Wollongong University from the School of Electrical, Computer and Telecommunications Engineering. So if something goes wrong with the presentation, please bear with me. I'm just kind of trying to operate a few things. I'm hoping I can play a couple of videos, a few videos at the beginning. So just to set the scene, if they don't work, please forgive me. So let's have a look. Let's see if we can go. Okay. So the presentation effectively has three main parts. Okay, the first part is laying out the landscape, what's been happening in IoT and 5G in space. And the second part is I'm going to be speaking about some of the work we've done with antenna design and some of the other work out there with pico satellites, very small satellites. And the last part is I'm going to talk about, just very briefly, about reflector arrays, which is an advanced solution. So effectively, what I'm trying to do is, or how the presentation is set up, or the message I'm trying to get across is that we have IoT, Internet of Things, we have 5G, but it's time to move these into space and provide connectivity. And I'm presenting as enablers small satellites, CubeSats to be more specific. And for antennas, I'm proposing that we use reflector array antennas to enable those solutions. I know, space constellations or satellite constellations have been around. I was around, I remember when in the early 2000s, when I was working with Motorola, the very first space constellation of satellites, or the business one, was put up, Iridium, and it went bankrupt very quickly. They wanted to charge people $10 a minute. They wanted to charge people $10 per minute for voice communication. It was knocked out by the simple 2.5G and the roaming at the time. So space and space constellations have been around for a while, but there has been changes recently, and there is different sense of the technology. Sometimes things are ahead of their time when they are first proposed. So Iridium is still up in space and it's still working, and sometimes you might see it branded under the Thuraya network, but now you have a few more players in there. So let's have a look at the first part of the talk. Let's have a look at the Internet of Things and what's happening in space. Everyone's going to space. So if you turn on the news, it's either Bezos or Elon or Sir Richard Branson. Everyone is trying to get on their spaceship and head to space. While it looks like these things sound like gimmicks, or it sounds like, just using space tourism, this is a huge leap and a huge enabler for communication technologies. And so you've got, in terms of the companies being involved, you've got SpaceX, you've got Amazon, and I believe you have a consortium around Virgin, Richard Branson, called Web1. I'm not sure if they're still going or not. These are all putting up or have started putting out low Earth orbit space constellations to provide internet connectivity. So the most famous one is the SpaceX Starlink, and hopefully I'm going to try to play a couple of videos with that. The links are there. I'm not sure if you can copy them. With Amazon, it's a Cooper system, and with Virgin it's the OneWeb system. And the reason I wanted to play those videos is just to give an idea to everyone and just to set the scene. But before I do that, it's worth mentioning why now, what's happened in this area that it's allowed space to become so cheap, so to speak. So cheap. Not long ago, 2 decades ago, space was really just a domain of NASA and a few other government players. Space is very expensive, took years, decades to plan space missions and so on. What really happened effectively is Elon Musk. That's what happened to space. Elon saw an opportunity, that a market that allowed a different way of doing things that would allow the price per kilogram of payload to go into space to be somewhere between 10 times to 100 times cheaper. And the way, very quickly, the way he managed to achieve that was by using off-the-shelf components and then testing them to become space compliant. For those of you involved in maybe in the space industry, there are special conditions for electronics to be able to head into space. So that period of 30 years, electronics have advanced so much that they've become good enough in most cases for space applications, even while they were built just for normal applications. So that's one avenue. The other thing that allowed basically the space to become so cheap is not talked about too much. What he actually did was break the business model or the supply chain model of building satellites and building rockets. Previously, you would have anywhere from 1,000 to sometimes 10,000 different suppliers for all the different parts that would make up a space vehicle. What he did was he reduced that right down, and he used 3D printing and metal 3D printers and designed a lot of the components in-house, which is kind of against everything that usually happens when it comes to the old method of specializing in something, providing certain specialized equipment. So these two things allowed now us to kind of make space cheap, and for people like me and many other researchers out there to build small satellites, and for costs of anywhere from $20,000 to $50,000 to put up a small satellite. So let me see if I can the first video is just a deployment. If it doesn't play, I'll hopefully it'll play. Let's see if I can share. So this should be sharing just a YouTube video, and I'll play.
Starlink satellites into low Earth orbit, or LEO.
Acquisition of signal.
Let's listen in for the call out of payload deploy.
Starlink deploy confirmed.
And we've confirmed deploy of the Starlink satellites. Now you can see the satellites, the Starlink satellites out in space drifting away from the second stage. As a reminder, this is just their drop-off orbit. Shortly, they will deploy their solar array, and over the next few days and weeks, they will distance themselves from each other and use their onboard ion thrusters to make their way into operational orbit.
And so you see, in one rocket launch, there were 52 satellites deployed, and you can just make out the different players. Each one is a satellite, and they'll just separate themselves out. And now, how many, to cover the whole globe and to give internet connectivity, how many satellites do you think we need to do that? Maybe you can pick a number in your mind. Apparently, for the Starlink, we'll need 42,000 of these satellites. So this is a bit of a longer video, but I think it's worth kind of sharing, and it's worth kind of listening to it as it sets the scene to what we're going to be talking about next.
You may live in an area with limited providers or network speeds, you still have internet accessibility, which can improve everything from entertainment to work to education and to healthcare. But 41.3% of the world doesn't have access to internet at all. And that's where SpaceX comes in with Starlink, which is getting very close to launching their own service. What is it? What are the latest developments? And why should you even care? I'm Matt Farrell. Welcome to Undecided. So as I mentioned, internet access isn't ubiquitous. Just over 40% of the world doesn't have any access to the internet yet. And even in areas with access, it can be spotty if you're not in a more urban area. Places like Africa, the Middle East, and Asia are lagging behind areas like North America and Europe. Laying long cable runs into remote regions can be costly given the number of potential customers. Even building out wireless signals in those areas is costly, which is why there are still so many low bandwidth areas in places across the United States. While 96% of urban areas have access to broadband, only 61% of rural areas do. Satellite internet service solves part of that problem because you can cover a large area with a single satellite, but there are some big downsides. Current satellite-based internet services are using geostationary satellites that are orbiting at over 35,000 kilometers, or about 22,000 miles, above the surface of the Earth. It's that distance that creates the first major problem: latency. A radio signal takes about 120 milliseconds to reach a geostationary satellite, with another 120 milliseconds to relay that signal back down to the ground. So in theory, you'd be looking at least 240 milliseconds. But in practice, you often see a round-trip latency between 400 and 600 milliseconds, 12 times slower than what you see on the ground. And then you have the challenge of how much bandwidth a single satellite can handle at once, which can affect the download and the upload speeds for everyone sharing that satellite. That means your maximum upload and download speeds will be likely on the lower side, and you'll have some data caps to contend with each month. Viasat and HughesNet are two of the options that you have available today, and they cost between $30 and $150 a month for speeds between 12 and 100 megabits per second. And Viasat's current throughput in their satellites is about 260 gigabits per second, which is shared by everybody using it. What this means is that there's a huge opening for competition, and that's where SpaceX comes in with Starlink. Since we already have satellite internet, what makes Starlink different? It's a low Earth orbit constellation of satellites that operate around 1/3 to 1/100th the height of geostationary satellites. As of April 22, 2020, there are 422 satellites in the Starlink constellation so far, with most of them deployed at around 550 kilometers or 340 miles. They're trying to launch 60 satellites per Falcon 9 flight for a total of around 4,400 satellites in Phase 1. And they'll add another 7,500 in Phase 2. So around the year 2027, they'll have nearly 12,000 satellites deployed in 3 orbital shells. Now, it's not guaranteed, but SpaceX has also submitted paperwork for an additional 30,000 satellites beyond that. So why so many satellites? Well, low Earth orbit satellites being much closer to the Earth means they can't be stationary. They have to move faster to maintain their orbit, and they will also have a smaller cone of coverage. But a big benefit of being so much closer is a much lower latency for communication. It'll have latencies around 25 to 35 milliseconds, which makes it comparable to cable and fiber optic networks. However, when using lasers to communicate between satellites, which Starlink will eventually do, it gets a little physics boost. Light travels through a vacuum about 47% faster than through glass, like a fiber optic cable. So even when accounting for transmitting from the planet and back, the faster laser transmission speeds between the satellites will give the network a latency edge compared to long stretches of fiber on Earth. And each satellite will be able to handle 1 terabit per second, which is almost 4 times the capacity of Viasat. That's roughly 40,000 people streaming 4K video at once. While all of that sounds incredible, This isn't a service that's meant to knock out terrestrial internet services. It's a service meant for a smaller segment of the market, which is primarily areas less densely populated. Just this past March, Elon talked about just that at the Satellite 2020 conference.
The challenge for anything that is space-based is that the size of the cell is gigantic. You know, so it's like I said, it's great for very low to maybe medium sort of sparsity situations, but it's not good for high density situations. We'll have some small number of customers in LA, but we can't do a lot of customers in LA because the bandwidth per cell is simply not high enough.
With tens of thousands of satellites being put into orbit, it's going to dwarf everything that's come before. At this point in our history, we've only launched about 9,000 objects into space. And of those, a little less than 6,000 are still in use today. SpaceX is going to triple that number in 5 to 7 years. And if they move forward with the additional 30,000, you can probably understand why a lot of people are concerned about overcrowding and space debris. If you've ever seen the movie Gravity, then you probably know about the Kessler syndrome. It's the theory that an object colliding with another in a densely packed area of space could cause a cascade of destruction. The FCC required very strict plans from SpaceX to mitigate space debris, which meant achieving a higher level of deorbiting reliability than NASA uses for itself. That's 90% of satellites reliably deorbiting. With a targeted lifespan of 5 to 7 years, SpaceX told the FCC that it will implement an operations plan for the orderly deorbit of satellites nearing the end of their useful lives at a rate far faster than is required under international standards, and that SpaceX satellites will deorbit by propulsively moving to a disposal orbit from which they will re-enter the Earth's atmosphere within approximately 1 year after completion of their mission. About 95% of the satellite's parts will disintegrate in the Earth's atmosphere as they deorbit. There's also been concerns about the impact on astronomical observations, with the satellites being very visible when they're deployed and also noticeable as they're tumbling their way to their final orbit. Astronomers are worried about the light pollution. SpaceX has been working with astronomers to address these concerns with strategies like painting sections of the newer satellites black to reduce the reflection, or adjusting their orbit orientation to minimize how the satellite will catch and reflect sunlight towards the surface of the Earth during their orbit, and even adding a sunshade to the satellite to help block reflections. They're calling it VisorSat. There's still a lot of outstanding questions about how this will ultimately impact visual and radio telescope observations, but SpaceX is actively trying to address them. And SpaceX isn't the only company working on low Earth orbit constellations for internet service. Companies like Telesat, OneWeb, and Amazon all have plans, but nobody has successfully launched a business out of this. Amazon is working on Project Kuiper, which will have around 3,200 satellites, but has yet to put any satellites into orbit. And OneWeb, which launched 74 satellites, just filed for bankruptcy in March of 2020.
I mean, it's real important to just set the stage here for LEO communications constellations. Guess how many LEO constellations didn't go bankrupt? 0.
Right.
0. Iridium's doing okay now, but the Iridium 1 went bankrupt. Orbcom went bankrupt. Globalstar bankrupt. Teledesic bankrupt. Am I leaving anyone out? There's a bunch of others that didn't get very far that also went bankrupt. Anyway, they all went bankrupt.
So you're focusing on making it work first?
Not bankrupt.
There's a huge business opportunity here for the company that can get up and running first, which is obviously looking like it's SpaceX. In 2018, they estimated the total cost would be about $10 billion, which is a lofty price tag for a company that's only expected to make $3 to $5 billion a year from launches by 2025. The projections for yearly revenue from Starlink are $30 to $50 billion a year by 2025. But that's a means to an end for Elon and SpaceX. In a media call before the launch of the very first Starlink satellites, Elon said, "We see this as a way for SpaceX to generate revenue that can be used to develop more and more advanced rockets and spaceships. We believe we can use the revenue from Starlink to fund Starship," which leads right into their goal for becoming a multiplanetary species.
There are really two fundamental paths. History is going to bifurcate along two directions. One path is we stay on Earth forever, and then there will be some eventual extinction event. I don't have an immediate doomsday prophecy, but eventually history suggests there will be some doomsday event. The alternative is to become a spacefaring civilization and a multi-planet species which I hope you would agree that is the right way to go. Yes?
Back on Earth, we're not going to have to wait too much longer to see Starlink in action. But before I get to when Starlink is actually going to be available, it's a good time to talk about getting a VPN for your internet.
Thank you for bearing with me for that one. So let's go back to our presentation. It should be on this one. Okay, hopefully everyone can see that. And I just wanted to play that because, you know, in a very, maybe I think 8 minutes or so, it kind of encapsulates all the complexities and all the different things that come with space. And so and before I get to this guy here, before I start talking about the bird, it kind of encapsulates everything about that. And what that Starlink is talking about, it's enabling us now, it's going to become okay to have these networks up in space, but they're not 5G networks. So they're not going to be interoperable with what's the technology that we have, the 5G, and now we are working on the 6G networks. And there's a bunch of other applications where people are putting up satellites. So there are more applications than just watching TikTok. So I've got this, you've got what's known as Animal Net. And there's a satellite out there that simply does IoT applications and literally tracks the antenna. I'm not sure if I can use, so literally, I'm not sure if they've got these poor birds, they've got this device on their back, and that's being tracked by the Icarus satellite. And it's actually a single satellite covering quite a large area and trying to kind of track these animals. So there's a bunch of applications out there that are referred to high bandwidth applications, what the Starlink is, and the other bunch of applications are Internet of Things, low data rate applications. For example, for this one, it's actually only at hundreds of bits per second in tracking this. And there's a bunch of actually there's a bunch of missions that are purely IoT missions going up into space. So having said that, having set the scene, so what is the case now for 5G and IoT in or / from space? What are the different problem areas that need to be solved? And what makes the case so compelling going forward? The first one is just traffic offloading. So even when people have deployed, companies have deployed in Australia 5G front-end capacities. So your capacities in Australia, the highest I've seen it on 5G is 200 megabits per second. Even at those speeds, companies have had to throttle back from the advertised 1 gigabits per second, because even with an upgraded back end or backhaul, they are having trouble with meeting the front end demand. So you want a back end network that can offload some of that traffic. That's the first problem. The second problem is just the coverage problem. You've got an exponential growth now in IoT devices being deployed, especially in regional and sparse areas. In Australia, we have quite large open areas. In Southeast Asia, there's this very similar as well, as these low data rate, low power devices come into play. You've got a coverage problem. So your normal terrestrial, i.e. land-based networks can't cover that. And a satellite network can do that job. The other thing is the need for network survivability. Notice we couldn't, unfortunately, hold this conference face-to-face. I had to come in to my office in the evenings because I couldn't trust my home network. So you've got this survivability, and we wouldn't actually be able to kind of carry on almost with this pandemic going on if we didn't have these digital connections. So space adds this layer of insurance or layer of survivability that is not on Earth, that allows networking to continue. Basically, the highest growing area, as one mentioned in that video, is basically high definition streaming, 4K, 8K videos, and the downlink part of satellites lend themselves well to that, like a downlink solution. It's easier to stream down on those downlinks. And we are heading towards a connected autonomous vehicle world. And if we want those vehicles, whether they are UAVs or whether they are on the ground, if we want those vehicles to reach that kind of peak of having these vehicles talk to each other, being connected to the network, and have them work in regional and sparsely connected areas, you'll need some wireless. You need some kind of space network for that. There are many places in this country where there is no wireless coverage. So if you have an autonomous vehicle, or if you have going forward, that will be disconnected from the network. And last but least, I mean, these are just a few of the applications, few of the motivations for this, is when you're looking at smart power generation or delivery in the networks, when you're monitoring network assets and you're trying to kind of ensure survivability of these very important networks, you need the network not to be as part of on the ground infrastructure. So if something happens to that network, well, your power network, the same thing will probably happen to your wireless network as well. So you need to kind of deassociate those things. So the reason we're mentioning 5G and not some general and IoT or IoT protocols is we want to try to kind of integrate the two networks. We want to integrate the same protocols that run your normal 4G/5G phones and your normal IoT, LoRaWAN as an example. We want to put that on satellites, so it becomes a seamless connection between those two. So what's the system requirements for 5G, and is it possible to actually have a 5G connection from space? So if we quickly define what 5G is, you've got 1 to 10 gigabits per second throughput, 1 to 10 milliseconds latency. It's aiming to support per cell 100 times more devices than your 4G, 1,000 times more capacity, and try to have 100% coverage without any black spots. And so the solutions on Earth, or terrestrial solutions, you have been implemented for 5G, are your high gain antennas, your adaptive beamforming. We went higher in the spectrum to millimeter wave spectrum. Maybe I can use this. More efficient frequency use, reuse, and massive MIMO. So these are some of the areas that brought to fruition 5G technologies. And just to stay with the spectrum, in 5G, you've got 3 kind of sections in the spectrum that support 5G. You've got the low end, the 600 megahertz to 2.6 gigahertz. So this is because 5G also was intended to support IoT applications at low data rates. So this is where that would sit. Up to 2.6 gigahertz, you're still talking about cellular frequencies, so things that you can carry around as a mobile phone. There's a higher band that's dedicated there also for cellular frequencies between the 3 to 5 gigahertz range. So there shouldn't be any issues, and has been shown there isn't any issues. Everything works at those frequencies from a cellular perspective. And then you've got the much higher frequencies. People like to kind of talk about those frequencies a bit more, kind of line of sight type of frequencies. But they've been shown to even work even with cellular kind of devices, but mostly these frequencies will be used for downlink, uplink, or point-to-point links. Just below there's kind of a bit of a background in terms of talking about, you know, the throughput. The lower frequencies, obviously, they'll support lower data rates. There's less bandwidth available there. And then as you go higher, there's a bit more bandwidth available to exploit in terms of the baseband there. And in terms of antenna size, the lower frequencies obviously have the larger antenna size, as that poor bird was carrying a longer antenna on his back. And as the frequencies go up, you'll have a smaller antenna size, and so on. But also we have to be careful that even weather starts affecting the network performance a lot more when we are talking with the higher frequencies. Okay, so is it possible to support, from a protocol perspective now, is it possible to support 5G? So there's a couple of working groups now that have been set up inside the 3GPP standards organization, which defined the 5G protocol. And so they're known as New Radio over NTN. There's also a European effort known as ESA that's also working in this direction. And what they're trying to do is actually define the protocols that would allow both direct access, so from a handheld device up to the satellite, and from a base station up to the satellite. That's mostly where most of their work is directed at, with trying to solve that backhauling problem. So instead of setting up point-to-point links, using, let's say, microwave links, or using fiber optic lines between towers, you can use low Earth orbiting satellite. So this will allow to, you know, solve some of the remote coverage problem. It will solve some of the traffic offloading problems, and it will give high bandwidth line of sight links. So now the next question is, do we go for low Earth orbit or geo centered? There's a big distance, as that video kind of explained, between the two. You're talking, you know, LEO could be anywhere from 300 to 600 kilometers, while your fixed satellites have to be out 35,000 kilometers. So it has to be low Earth orbit. It really cannot. We can do IoT from long distance away with high gain antennas, but if we can support the delay, but it really has to be those clusters, those constellations. But you see, a single company like SpaceX, like as that video is saying, wants to put up 42,000 of these satellites. So that is an interesting question that we have to kind of keep in the back of our mind. There's a lot of kind of things that go around there. So if we summarize now, what are the different, oops, not sure why it jumped. I think this one has maybe a play. So maybe I'll try to pause it. Yep, let's see if it can pause this. Oops, it wants to keep jumping ahead. Anyway, this table comes from one of our papers and just kind of classifies the different satellites. What we are hoping is we can actually reduce the size of the satellite further and hence reduce the cost. So what we want is to be working in this small satellite space here at very low powers and very low cost. So we want to be working in the hundreds of thousands of dollars rather than the millions of dollars. So if you think about this would allow effectively almost any company, even small enterprises, to put up their own satellite constellation for their own communications needs. If we kind of make it interoperable, if we can run the 5G standard onto the satellites and not run a proprietary kind of protocols and proprietary kind of receivers on there. So a candidate for these pico satellites are CubeSats. So many of you would have seen it. I'll just quickly run through that. CubeSats, and the reason I'm talking about CubeSats is we've built one here in our laboratory, and I'll give you a photo a second. With it, it's the very small 10 by 10 by 10 centimeter cubes. They weigh about 1.3 kilograms, and just designed off the shelf components. They only cost about 20K to build. Traditionally, they were just set up, or initially they were set up just to teach aeronautics. Something's gone on in my presentation. I'll pause it here. Let's see if that works. As this started about in the early 2000s, just in the aeronautics department, but they have really grown into something else now, and with much higher powers, much more capability. But they present their own kind of challenges. But what we want to do is really head down that path. What we want is to see if we can build these small satellites and support these 5G bandwidths. So this is the UOW satellite. This is a 3U. You can see there's 3 cubes stacked on top of each other. It has slightly different, more capabilities in terms of its power use, and in terms of its power use and sophistication. So it doesn't only do solar panels. If you notice here, these guys are actually radiators as well, to get rid of the huge amount of heat we've built this satellite to withstand, as in we've built it in such a way that can actually run with quite high power, so into the hundreds of watts. In normal pico satellites, they're only running in the ones to tens of watts. So we've built it with high processing power and high powered antennas in mind. So if I can just go to the next. So this is the first kind of version of the satellite sitting on its stand in the laboratory, and it's sitting inside inside the chamber, the ECM, to measure the radiation patterns. Space is not cheap, but it's become cheaper. So space is not cheap, but it has become cheaper. So it is expensive to a point to set up some of the equipment, but it's not overly expensive. The biggest problem we had in setting up the chamber, the 3-meter measuring chamber here, was actually finding the space for it rather than the cost. They're quite large, they're heavy, it weighs 25 tons and so on. So the idea would be to mount an antenna and a radio that would give us the 5G onto these satellites. So another thing we built was our own radio. So this operates at 2.45 gigahertz. It fits nicely, snugly within the CubeSat, and at the moment it can give us 60 megabits per second. But we are developing a 2.0 version in the X band, and we're hoping to get up to 1 gigabits per second speed out of it. And so this particular one works in a few watts, very low power, and in standby mode. And we did, if you're interested, we published this in JMAS. So it's kind of like a step guide to how to build this thing. If you're interested in this type of area, it's in IEEE JMAS, or the Journal for Miniaturization of Air and Space Systems. And interestingly, it is, for whatever reason, it's the most popular article there. So I'm not sure why. Maybe because it's a guide how to build something. I'm not sure why. But we're kind of proud of that one on there. So, but if we jump now to, there's been quite a lot of antennas and antenna proposals. And again, we recently published a paper grouping all of those different, so the missions that went up into space. So these aren't just things that sit in the laboratory. These are just specifically antennas that have been proposed for CUBE satellites or versions of CUBE satellites that have planned to go on missions into space. And so you can see a big range of from very simple planar type antennas to your parabolic reflector antennas to helical and so on. If we look at the last one, actually this one comes from Jet Propulsion Laboratories. It's an interesting one, and the reason I picked it out because it is related to the reflector arrays that we're going to be talking about previously. So this is an 18U CubeSat. You can see 3 CubeSats, 3 there. So it's 3 by 4. Maybe it's not 18. I can't. 12U CubeSat. And it's got a very interesting deployment mechanism. But you can see how complex the deployment mechanism is to get this type of very very high gain antenna deployed. It's a very interesting design. Notice but the parabolic shape, and this parabolic shape has to be actually done perfectly for it to work and to point in the right direction. So just keep that in mind when we speak about reflector arrays later. So if we're going to design an antenna system for 5G, so these are some of the antenna requirements that we need. So K-band, very high gain, and has to be kind of low cost, compact. So it's actually very difficult problem, very difficult problem to solve, and hence I think there's a rich place to do research. There's a rich place to kind of collaborate in this area, and so you've got kind of 2 candidates. You've got your phased array antennas, which can allow you to do high gain and allow you to point the beam. But that requires quite a lot of processing power and quite a lot of fiddling going on. And then you've got reflector, normal parabolic reflectors, but deploying these reflectors with the small satellites, they're quite difficult to do. So what we are proposing is, why don't we, so this is, we did not obviously invent, obviously not reflector arrays. What we are proposing is that we use reflector arrays on CUBE satellites. And the way a reflector array kind of works, it kind of combines phased arrays and a parabolic reflector, but now the reflector itself is not parabolic anymore. If you have a look at this reflector, it's actually flat. And the feed, which is here, for example, actually that can be placed anywhere now. So it gives you that freedom to place this. So now when you're deploying this type of system or you're installing it on your CubeSat, you have a lot more freedom and a lot more kind of flexibility in how you do this. And the way, so effectively what we want to do is build a reflector array that can go onto our CubeSat, and then hopefully that will be an enabler for the 5G. And reflector arrays, the first kind of reflector array started, there was one paper published in the 60s, then people forgot about them. And until the late 90s, when someone built a reflector array on with PCB small patch antenna reflectors. So the first reflector array here you see is actually just shorted kind of waveguides, and you might be thinking, okay, how does this kind of, if you're not from the wireless area, from the antenna area, how does this kind of work? Each one of these waveguides actually is just slightly different length, and they have those slight, and they go out at slightly different lengths in proportion to the center frequency that you're trying to transmit at. And what that does, it compensates for the position of that feed horn antenna that's pushing in. And the effect that it has is it actually points, then allows you then to point the beam into a pencil beam, which is actually much, much tighter than your normal reflector. And so these are passive reflectors. There's no electronics stuck here. They're just simply PCBs with different patches on them, and you've got a feed that's kind of pushing a waveform into that. So that's, I won't go into, just very quickly, you have an incident wave, you push that onto the passive reflector, then you get a reflected wave coming back, which is a combination of the different, it's a combination of the different phases that I spoke about. It's a combination, and then it allows you to kind of point the beam. So you can muck around with these, each of these patches. So let me just jump to the patches. So here, each one of these patches, there are different ways of designing these patches, and there's been quite a few proposals now how you would do these patches. But by having different sizes, this also allows you to have different phases, and this also allows you then to compensate for this change in incidence, the position of the incidence, and allows you then all the different reflections will add into a particular point. So you can make, it gives you quite a lot of flexibility in there. So that's where we're at with that. So we're in that process of building this particular antenna and testing it in our chamber. I'm just kind of, I'm aware of the time, so I just want to kind of leave some time for some Q&A. Yeah, so that's where we're at, and we are hoping that this area will be kind of a rich area of research and quite a fundamental area where we can make contributions for quite a few years to come. We also have a special issue. If you are interested to publish in this area in electronics, and we are more than happy to also to collaborate. That's my email address there, and I'm happy to have any discussions or questions. And so excuse me if I went on a bit too long.
Thank you very much. It was really a nice presentation, and the content is very resourceful. I like the content very much. So now I would like to ask the audience if they have any questions. The floor is to audience and open for question session. Dear audience, you may raise your hand through Zoom, or you may ask question directly. Professor Raad, I have a little question, small. Actually,
okay, no.
Normally I don't work in communication area.
Sure.
So maybe the questions will be very light, but my simple question is, what is the difference between cube satellite and the regular satellite? So that means the working principle, I get idea from your presentations that size is little bit smaller than the regular satellite, but I think this is not the actual difference between those two satellites. So if there is critical difference between these two satellites, so I want to ask this question.
Thank you for your question. No, it's no big. It's a very good question. It's the cube satellite. Yes, you've got the size difference, but the cube satellite you can build in any university laboratory. So you can build in. You don't need a clean room. You know, you don't need a very sophisticated, very expensive lab to build, and you can build it using off-the-shelf components, so it's cheap. And so it doesn't cost more. You know, some of them cost as little as $20,000 compared to normal satellites. The minimum cost usually is around the $10 million mark for your normal communication satellite. And so there's a big cost difference. And so this way, with the small cube satellites, it allows, you know, kind of almost like classroom level space access. It allows, you know, it allows, you know, normal. I've got my lab here. The students, you know, the cube satellite that you saw, it's a 3U. It's a satellite. You know, undergraduate students use it, and postgraduate students use it, and companies, you know, use it. So it's kind of allows for multiple things, and also it's the way they are deployed. They're actually very simple. The way they are deployed, they're actually loaded up into like a fridge-like container, and they are kind of, that's the reason they have to be a standard size and weight, and they are loaded in a spring-loaded mechanism, and they just kind of flung out into space in a very simple way, and they're designed to be carried as extra baggage onto space missions. So yeah, sorry, go ahead.
Yeah, that means yeah, that means it's a prototype of you are having a space in your lab with a satellite, like that prototype.
Sorry, yeah. So you can have it in your lab.
It's like a prototype. That prototype you create in your lab. So you can give the idea of space to among the students, graduate students, undergraduate students, similarly like that. It's really nice.
Yeah, but also you can actually, that same satellite, you can build a flight-ready version of it. The same one that I showed you. You can have a flight-ready version of it and put it on a spaceship and take it off to space. So it's
it's nice. Now I get the idea. I have another one question that just I am interested to know that about the inter-satellite communications. You showed that there is a plan that there will be around 42,000 satellites in the space. So how the satellites will communicate with each other, or they won't communicate at all? They will communicate with geostation through geostations, or the satellites will communicate between themselves. So is there any eyes? Because there will be huge traffic jam, I think.
That's right. But there's a lot of space in space. Sorry to use that.
Yeah.
There's a lot of space. So even 42,000, even the number sounds like a lot, but the Earth, and you know, it's quite large. So if you divide up, you know, how many satellites you will, you can have hundreds and hundreds of thousands of these satellites out there. But if you noticed in that initial video, the Starlink one wants later to use lasers. So they want to use laser communication. So point-to-point laser communication. That has its own difficulty, because trying to lock on another moving satellite, that's its own difficulty. But the reflector arrays we are proposing to use actually will allow you to do satellite-to-satellite communication in a very very nice way. And so because it allows you to focus the beam very tightly, so the angle of the energy of the beam can be focused very tightly. It will not be as tight, obviously, as a laser beam, but it's along those lines. So it can be built to do that. So as long as you are doing that and pointing towards the satellites themselves, you shouldn't, you know, they shouldn't interfere with each other. Actually, on Earth we have a lot more interference from terrestrials.
There will be huge interference, because every satellite will try to communicate with each other. So the bandwidth should be divided among all the satellites. There should be regulatory body somewhere. I don't know, because the frequency should be allocated to each satellite. Otherwise, there will be huge interference and the communication won't be possible. I don't know. Those are questions coming to my mind. through your presentations. So I
Yeah.
just accept. Again,
there's a question from Afifa. There's a question from Afifa. If we tested the reflector array? No, not yet. We haven't tested the reflector array. That's new research that's coming. It's coming out.
also,
It's actually quite complex to even simulating the reflector array. The simulation tools are quite limited for reflector arrays, even simulation. So we are in the process now. We have partnered with a local company, and so we'll be building that reflector array. So we'll build it to test it, rather than we're doing it the old way instead of simulating to find out how it works. So we're just modeling and then building. So,
there should be some multiplexing access protocols to communicate. I think there is huge working space, I think, nowadays to have research. So I think your presentation will create a new arena to the audience who is interested in communication areas.
yeah, look, I know the conference, that maybe the subject matter is more about Industry 4.0, but I know from my understanding of Industry 4.0 and look, we're moving towards a completely connected, machines, and without a layer of that's sitting above that, there's always going to be connectivity. So satellite constellations will play a very, very important part in this I was going to say space. I'm just going to say this area.
Yeah.
Without the silly puns. Okay.
Yeah. That's really nice. Dear audience, do you have any questions to our guest? Okay. I think the audience don't have any questions. Dr. Mahmoud Hassan. So now I can give the floor to our co-chair, Dr. Mahmoud Hassan Imam. Are you listening to me?
Yeah, I'm there.
Okay. Carry on. Introduce yourself and carry on.
Okay, thank you. Thank you. Thank you for the nice speech. Actually, very informative. I think it's a little bit advanced for us, for the audience here. This is a little bit advanced work, so that's why we don't have much question. I just have one. Yeah, I have just one question, Professor. About I also not very much familiar in this work because my area in bioengineering, like signal processing and other things. But I have a little query about if anyone is interested to contribute in this area. What are the main areas? Like do you suggest these areas they should move on so that they can contribute? Like you were talking about a lot of antenna designs, and the cube satellite design. So these are the areas. Are you preferring, or any other student who's going for starting his PhD? So which area should you focus for his background study?
Thank you for that question. It's look, it's like I said, it's a very rich area, and if if we're going to talk about the protocol stack or the communication stack, there's problems to be solved at all of these levels. So the antenna is the lowest of the low in terms of the protocol stack. It's the physical medium. So but if you're talking about in terms of the next layer up, in terms of the signal processing, so we presented the paper with the SDRs, the software defined radio, and the signal processing. How do you do that in space? You can't reprogram stuff in space. How do you use the least power, and so forth? There's a lot of there's a lot of constraints in space that you just don't have on Earth. So even your normal algorithms, even your normal signal processing, or even your famous algorithms for signal processing, all of a sudden become an interesting research topic if you put them up, and you need to carry these out in space on limited resources, limited memory, make them survivable. Even the electronics, even when they are shielded, they are still affected by solar radiation, which may affect sometimes some of the outputs. So you have to, in terms of even just simple things that you would never even think about on Earth. So there's actually quite, as you move up in the protocol stack, every part of the protocol stack there is actually problems to be solved. And I'm not. This area, this whole space satellite area, is now the new race in terms of research. And you'll see many countries. Australia, we've come a bit late to it. We only set up our space agency 2 years ago now. And so we've come, but the government is pouring money left, right, and center into it. Many countries are pouring money into it. And, there's many reasons for that. Some of it is geopolitical. No one wants to be left behind. And it's really a big frontier. So I would encourage, students to look at this area. And I'm more than happy to kind of, if people are interested to discuss further, I'm quite open to either talk to myself or point you in the right direction if you're interested in topics along those lines.
Okay, thank you very much. Yeah, I got the point here. Thank you very much for your nice suggestion and your nice presentation. So I thank you on behalf of the conference for joining here.
Hassan Imam, excuse me. There is 2 questions to the guest. Please go through the questions.
Oh, so we have
in
some
the chat
questions.
box.
Yeah, I see.
I think I answered the first. I think I answered the question about the testing. I think that one from Afifa.
Okay, we have another from Shafayat Jamil.
Yes.
To user, how will you place the laser in case of 2 satellites are placed facing oppositely in align with sun? That's a technical question actually.
That's a problem, but I'm not a laser guy. the Starlink guys are laser guys, but yeah, you point, you set up the satellites in such a way, and even your solar panels, they're all synchronized with the sun. So they're always facing in a particular way. So your solar panels are always facing towards the sun on your satellites to pick up the most power, but your communication links have to be obviously facing, especially for laser links, in the opposite direction. So there's a lot of, there's work on there, but I'm not kind of a laser expert. I'm more, I stay at the radio frequencies side of things.
Okay, thank you, sir. Thank you for your answer. So I think we hope we can end the session. That's a very nice, informative session. So I thank you again for joining us from Australia in this pandemic time. And so there is thank you very much. And there is a digital a clock of appreciation I will giving normally at this time in conference. This is the new normal, the conference. So I thank you very much. Also, I give the floor to Mr. Mehdi Hassan for being part of the remaining conferences. Thank you.
Thank you so much. Thank you.
Thank you, sir. At this stage, our session chair, Professor Dr. Masuma Akhtar ma'am, will hand over a certificate as a token of appreciation to our honorable keynote speaker, Dr. Raad Raad.
Thank you so much, and thank you for that. Really appreciate that, and really I thank you for allowing me to speak to you guys at this conference.
Thank you, sir. Ladies and gentlemen, it is time to appreciate our honorable session chair and co-chair. I, on behalf of the organizing committee, feel honored to share the session chair and co-chair certificate to our respective session chair and co-chair as a token of appreciation. This is the certificate for the session chair. Ma'am, will you accept it?
Yeah, thank you very much to give me the opportunity to chairing the session. Thank you very much to the organizing committee of this conference. Thanks.
Thank you, honorable session chair. Now I would like to request our session co-chair to receive the certificate as a token of appreciation.
Yeah, thank you very much. Thank you. Thank you, ACMI 2021. I wish all the success of this conference, and thank you for inviting me to join the session co-chair of this conference. Thank you.
Thank you so much, sir. Ladies and gentlemen, this is time to capture this beautiful moment as a memory of a source for inspiration for the next edition of the conference. I would like to request all of you to open the camera to complete this photo session. Thank you so much. Thanks all of you for participating in this session and make this session live. With the permission of session chair and co-chair, I would like to close this session.
Yeah,
Thank you very much, Mehdi. You may close this session, and at the same time, I thanks very much our guest, Professor Raad Raad. Thank you very much. I appreciate your coming here and deliver your expertise, share your knowledge to our students among us. Actually, we enjoy your presentation very much. Thank you very much.
Thank you so much, and hopefully we can in the future we can do this face to face in Australia and in Bangladesh.
I wish we will see you in Bangladesh.
Hopefully.
Thank you very much.
Thank you.
Thank you so much, ma'am. Okay, madam. Thank you so much. Thank you all.
Okay.